Here we're going to analyze the fully implicit method for the diffusion equation. Okay, this is like the forward time-centered space method, except that the spatial derivatives on the right-hand side of the diffusion equation, the second-order spatial derivatives, are evaluated at time j plus 1. So, and in the explicit method, they were evaluated at time j. So here, this is the finite difference representation corresponding to the second order partial derivative of u with respect to x. And as you can see here, they are evaluated. We are using here the values of the u function at time j plus 1. And again, if we compare that expression with the one we derived for the explicit method, you could see that the u functions you were considering there, they were evaluated at time j. So that's the only difference with respect to the explicit method. Because actually, for example, the finite difference representation for the partial derivative of u with respect to time, it's actually the same. And actually for the accuracy of the representation, it's the same as well. So that's the only difference. But that difference is going to introduce important consequences in this method, in this fully implicit method. So as we are doing, I mean, it's important also to have like a picture of this method, this fully implicit method. These are the dashed line connects the 2 points in the partial derivative of time partial derivative, and this straight line are the points which are connected in our finite difference representations. The point connected by the second order partial derivative with respect to space. So as you can see here, these are the points. The open points are the ones that we want to evaluate as considering the value of the u function at previous time step. As you can see, there are several of them that the ones that they are unknown, and just in principle there is one that we do know. So in this method, actually, what happens is that we can have an expression, we can clear actually the value of the u function at time j as a function of the other u functions evaluated at other time at j plus 1. But there is no way of having an expression for the u function. There is no explicit way, at least in this way, to have an expression for the u function evaluated at time j plus 1 as a function of the u function evaluated at time j as a function of the previous time step, as the one we had for the explicit method. So we have to deal with another way of analyzing these equations. That's going to be the matrix representation. So basically, again here, as we had in the explicit method, we do have like nx minus 1 equations. So that equation, we have to apply that equation for different n, and this n will run from 1 to nx minus 1. This alpha parameter here, again, as the one we had in the explicit method, is given by this expression, d, which is the conductivity, times delta t, the time step, over delta x squared. And the other two equations are going to be supplemented by the boundary conditions evaluated on both sides at n equals 0 on the left side and n equal nx on the right hand side. Here the next step will be to have a matrix representation, because in this fully implicit method, again, and we are not able to have an explicit expression for the u function evaluated at the time j plus 1 as a function of the u values evaluated at time j at the previous time step. That's why actually it's called implicit method compared to the other one, which was called explicit method.